Hey there, it's Shannon Math Chick Myers, and today we'll be looking at integrals involving the sine and cosine functions which have at least one factor raised to a positive integer. All right, so this is probably this whole section, which is 8.3 in the Larson and Edwards text, is going to be split into several parts. Make sure you watch all the parts to get the full amount of info. All right, so here we go. If the sine portion of the integrand has an odd positive integer and the cosine portion has any other power, then we save one sine factor and we convert the rest of them to cosine factors. So basically you are realizing that the sine function, with the exception of a negative, is our g prime if cosine is our u sub. All right, so actually if cosine is our g of x or whatever we're dealing with variable wise, then the derivative of the cosine function is the sine function. Yes, we need a negative, but you can adjust the integral by multiplying by -1 and putting -1 inside. Then what you do is you would end up with a situation where you'll have several terms and you'll have that g prime available. You expand and you integrate. On these, the angles need to match. If you want to evaluate a definite integral, you could either keep it going all along, or you can find the indefinite integral first and then back substitute depending on your preference. Cool? All right, so here we go. We've got that odd number of sine factors and an even number of cosine factors. So we're going to set one sine at x aside as a factor, and then we'll have sine squared at x. Now the cosine at x is going to end up being your g of x. That is squared. And then we have this sine at x dx available to use for our g prime. After we simplify, we'll adjust by the negative. Now, converting the sine factors to cosine factors, so we'll have sine squared at x is 1 minus cosine squared at x. And then we still have it multiplied by cosine at x, the quantity squared, times sine at x dx. Continuing, we will have the integral of, so I'm going to distribute this cosine squared at x to both. And not just that, I'm going to distribute the sine at x dx as well. I like writing it as separate integrals at first for folks that are a little uncomfortable. So we will get cosine squared at x. Sorry, I wanted to put it like this because we're going to be using the power rule. Cosine at x, the quantity squared, and then we have times sine at x dx. The next one we'll have minus, we have a cosine squared at x times a cosine squared at x. So we'll have the integral of cosine at x to the 4th power and then times sine at x dx. So in this case, our g at x is cosine at x, or you could think of it as your u substitution. So g prime at x is going to be negative sine at x dx. So we have the sine at x, we have the dx, but now we need a negative sign. And so if I turn the outside of the second integral to plus, that takes care of it. And I need it over here as well. So I'm going to put my negative here and a negative on the outside of the integral. And then I will have negative 1/3 cosine cubed at x, and we'll have plus 1/5 cosine to the 5th at x plus our constant of integration, and we're done. And then again, just to remind you, our g prime was negative sine at x dx, negative sine at x dx. Groovy? All right. Off to a wonderful start on our trip. Okay, so here we go. This one, again, we have an odd number of sine factors, and then we have that cosine factor in the denominator that's raised to, you know, it's a square root in the denominator. So that's the cosine 2x has to be our g of x in this case. So the angles match, so we're good to go on that. So here we go. Let's do this. We're going to have the integral of sine to the 4th power, our angle is 2x, times cosine at 2x to the, I'll put it in parentheses, negative 1/2 power, times sine at 2x. So in this case, our g of x is cosine at 2x. So be careful. G prime at x will be equal to negative 2 sine at 2x. It's really easy to drop those coefficients to the angles, so be careful. All right, but we need to do a little bit of conversion first. So this will be equal to sine squared at 2x, the quantity squared, the cosine at 2x to the 1/2, and the sine at 2x. Sorry, forgot my dx over there. And the sine at 2x will just be going along for the ride for a moment. Now, converting the sines to cosines, we will have sine squared at 2x. This is still going to be squared, but inside, that's going to be 1 minus cosine squared at 2x. Keep that angle going. And then times cosine at 2x to the negative 1/2 times sine at 2x dx. And expanding, we will have 1 minus 2 times the product of the ends. So 2 times cosine squared at 2x, and then plus the cosine to the 4th at 2x. So that's cosine squared at 2x, the quantity squared. And that's going to be times cosine at 2x to the negative 1/2 times sine at 2x dx. Now you can see that our g of x will be equal to cosine at 2x. So g prime at x is what? Awesome, negative 2 sine at 2x dx. So keep that in mind. We're now going to multiply through by this whole thing here into each of those 3 terms. So I'm going to move my equals a little bit out of line here. And then I'm going to write separate integrals. So the first one will just be cosine at 2x to the negative 1/2 power times sine at 2x dx minus 2 times the integral of, so I have a cosine squared 2x and a cosine negative 1/2 to the 2x, or to the negative 1/2. So what I need to do is have when I subtract those exponents, I will have cosine at 2x raised to the 4 halves minus 1 half is 3 halves. And then I have my sine at 2x dx. And then the last one, 4 is the same as 8 halves. So we'll end up with plus the integral of cosine 2x raised to the 7 halves when you combine times sine at 2x dx. Now each of these needs a factor of -2. So if you just multiply each by -2 and -1/2, you'll have your G prime. Which was -2 sine at 2x times dx. Groovy? Awesome. Okay, so now we'll have -1/2 times 1/2 is 2, and then we'll have cosine to the positive 1/2 2x. Minus a minus is plus. We're raising the 3 halves power will get to be 5 halves. So when you invert and multiply, you get 2/5 times cosine to the 5 halves at 2x. And then minus 1/2 times two ninths times cosine raised to the 9 halves at 2x, and then plus our constant of integration. And simplifying, we'll have negative cosine at 2x. I like writing the powers outside, so I'm going to do that. I think it just is more clear. And then plus 2/5 cosine at 2x raised to the 5 halves minus 1/9 cosine at 2x raised to the 9 halves plus our constant of integration. How are we doing? Doing well? Awesome sauce. All right, so we've done our part 1 of this part. So now we're going to take a look at what we would do when we've got the sine and cosine functions that have the same angle, and if the cosine portion of the integrand has an odd positive integer as a power, the sine portion has any other power, then you save one cosine factor and you convert the others into sine factors. So it's just the opposite of what we just did. And then we expand and integrate. So if you want to try these on your own, go ahead, pause the movie and check it out. Remember, the angles must be the same. So let's do it. We've got the same angle and we've got both of them are odd. Okay, both of them are odd. So do you see, with both of them odd, you could go the other way. But this time we'll turn them into sine factors just for a change of pace. So we'll have the integral of, since we're going to be changing these things into sine factors, I'm going to put sine at 5x, that quantity raised to the 7th, on its own, or in the parentheses like that. And then we have cosine at 5x raised to that fourth power, and then we're going to reserve a factor of cosine at 5x dx for our g prime. Now, this will be the integral of. We'll leave this sine at 5x raised to the 7th alone. Cosine to the 4th at 5x is the same as cosine squared at 5x squared. We cool with that? And then we have our cosine at 5x dx hanging around. This will be sine at 5x raised to the 7th. When I square the cosine, or no, when I rewrite, cosine squared at 5x in terms of the sine function, I will have 1 minus sine squared at 5x, and that quantity is being squared. And I still have cosine at 5x dx. Now, when I said before, oh, you could go either way with it, it's really the most wise as you see us trying to, work this to where I've got a big quantity to the 1 power. I wouldn't want to keep going on this with raised to the 7th. It's easier to do this on something raised to the 5th. It would work, but it would take longer. So this was a wise choice, in other words. So we have sine at 5x raised to the 7th times, when I square this quantity, I'll have 1 minus double the product of our ends, and then plus the last end squared will give us sine at 5x to the 4th power times cosine at 5x dx. Okay, so we said that our g of x was going to be equal to sine at 5x. So g prime at x will be, awesome, 5 times cosine at 5x. So keep that in mind. We're going to go ahead and distribute through, and remember, it's this whole deal here. You're going to be multiplying on the left side this, oh, and I'm sorry, I forgot my integrals. On the left side, the sine at 5x to the 7th, and to the right of it, we're multiplying this cosine 5x dx. So here we go. That will equal to the integral of sine at 5x, this quantity raised to the 7th, because I'm multiplying it to 1, times cosine at 5x dx, minus 2 times the integral of sine at 5x raised to the 9th power. Awesome. And then my cosine at 5x dx. And finally, we will have the sine function, so plus integral sine function at 5x being raised to the 11th. And then, sorry, I'm moving this over, my bad. Okay, and so then we will have times cosine at 5x dx. So now each of these is missing a factor of 5 to have our g prime. So we're going to need to multiply each of them by 1/5 and multiply by 5. And then we're almost done. So we'll have 1/5 times 1/8 sine at 5x to the 8th power, and then minus 2/5 times 1/10 sine at 5x, that quantity to the 10th power, plus 1/5 times, sorry, that's a 1, times 1/12 sine at 5x to the 12th power, plus our constant of integration. And then cleaning it up a little, we will have 1/40 times, these aren't as messy, so I'll just do sine raised to the 8th, and we've got at 5x minus, let's see, the 2 divides out some of that, so we'll have 1/25 sine at 5x to the 10th power plus 1/60 sine at 5x raised to the 12th power plus our constant of integration. Groovy? Awesome sauce. Okay, next up. Integrals involving only one sine or cosine function, which is raised to a positive even integer. All right? So this is a different kind of strategy. If only one sine or cosine function is in the integrand and has an even positive integer as a power, you can use the power reducing formula. Cosine squared at a equals 1 plus cosine 2a over 2, or sine squared at a equals 1 minus cosine 2a all over 2, until you can use basic integration formulas. So again, you can evaluate the indefinite integral first and then add on your and then evaluate your limits of integration at the end after you find your antiderivative. All right, so here we go. Let's do this. We only have cosine functions. So if you were to do like u equals cosine x, du is negative sine at x dx, you don't have a sine at x to do that. So we need to reduce this power. So here we go. We'll get the integral of, well, it's the cosine function, and I'll write this out first. We're going to end up with cosine squared at x, the quantity squared, dx. So now we'll have 1 plus cosine 2x, I'm doubling that angle, over 2. And that itself is squared. And we're integrating with respect to x. So when I square the 1/2, I can bring it out as a 4th. And then I'll have 1 plus 2 cosine at 2x plus cosine squared at 2x, all with respect, integrating with respect to x. Continuing, we have 1/4 times the integral of 1 plus 2 times cosine at 2x. Now we have to use that formula again. So we'll have 1 plus cosine. This time it's 2 times 2x to double that angle, all over 2. And then we'll have dx. So then, simplifying the integral slightly, we will have, do you see we'll have a 1 plus a 1/2 in the pink, which makes 3/2. And then we'll have plus 2 cosine 2x plus 1/2 cosine at 4x with respect to x. Okay, so let's work through it. This is going to be 1/4 times. We'll get 3/2 x, now I'm integrating, plus I have a cosine at 2x, right? And so I'm going to be dividing by 2. So I have 2 times 1/2 sine at 2x when I do the integration. And then plus, again, I need to have a 4 handy. So I need to divide by 4. So, or multiply by 1/4. So I'll have 1/2 times 1/4 times sine at 4x plus our constant of integration. And so simplifying, we're going to get 3/8 times x. These 2's divide out, so we'll just have 1/4, I'm bringing the 1/4 through, sine at 2x, plus we will have 1/4 times 1/8 would be 1/32 times sine at 4x, plus our constant of integration. Good so far? Awesome sauce. And then just a little example here. Find the area of the region bounded by the graphs of y equals cosine squared at x, y equals sine at x times cosine at x equals negative pi over 2, and x equals pi over 4. So here we go. X equals negative pi over 2 is this vertical line here. And then x equal to pi over 4 will be about here. So that takes care of these two. And then I'll just go ahead and plug in some points. We can do this guy in purple. And I'll plug in negative pi over 2. So cosine at negative pi over 2 is 0. And when you square 0, you still get 0. So we'll have a point here. And then if I plug in 0 for x, I'll get 1. And 1 squared is 1. So let me add in 1 and 1/2. All right. So I said I was up at 1. Now let's do a pi over 4. So cosine at pi over 4 is 1 over root 2, but when you square that, you'll get positive 1/2. And then we'll get the same over here because the cosine function is even. And so our graph will look approximately like that. All right, so now let's take a look at, I'm going green for this guy. Y is sine at x times cosine at x. So at negative pi over 2, we're at 0 because that cosine function will 0 out. At 0, the sine function will 0 out. So you have another point there. So at pi over 4, you have 1 over root 2, or if you want to think of it as root 2 over 2 for each of those outputs. And so you end up getting, and one of them is negative, so you end up getting negative 1/2 down here. And then at pi over 4, you'll be up there. So it'll look something like this. And so our region that we're interested in looks something like this. Cool, cool. And everything's in terms of x, so our representative rectangle, you can draw it anywhere, remember, it'll look something like that. Groovy? Okay, so now let's find our area. So the area will be equal to the integral from negative pi over 2 to pi over 4. The topmost graph is the purple one, and that one is cosine squared at x. And we'll subtract from that sine at x times cosine at x. And that's all being integrated with respect to x. So our area will be integral pi over 2, negative pi over 2 to pi over 4. What do I have to do with that cosine squared at x business? I need to rewrite it. Good. So that's going to be 1 plus cosine 2x all over 2 minus sine at x times cosine at x dx. All right, so now our area will be, I'm not going to bring anything out. So we're going to end up having, it's 1/2 plus 1/2 cosine 2x, right? So we're going to get 1/2 x and then plus 1/2 the antiderivative of cosine at 2x with respect to x will be times 1/2 sine at 2x. Now with this next one, if I consider raising the sine at x function to the 1 power, the derivative of the sine function is cosine at x, right? So I will have 1/2 because of the power rule times sine at x, the quantity squared. And then we're evaluating this from x is negative pi over 2 to x is pi over 4. Groovy? So our area will be, all of these have a 1/2, correct? So I'm going to go ahead and pull that out, and then we'll end up with, for our upper limit, we'll have pi over 4 plus 1/2 times sine at 2 times pi over 4 is sine at pi over 2. And that is just going to be 1. Minus 1/2 sine at pi over 4 is 1 over root 2, or root 2 over 2. When you square that, you get a half. Lower limit of integration. We'll have negative pi over 2, and then plus 1/2 sine at 2 times negative pi over 2 is sine at negative pi, which is just going to zero out. And then minus 1/2, again, you'd get the sine function zeroing out. So you'll just get times 0 squared, or 0. And then simplifying, we have 1/2 times pi over 4 plus 1/2 minus 1/4 plus pi over 2. Area will be 1/2 pi over 4 plus 1/4 plus pi over 2 will be if I bring out a 4 in the denominator, I'll have 1/8 times pi plus 1 plus 2 pi. So our area will be 1/8 times 3 pi plus 1 units squared. Groovy? Okay, so the next part deals with if you have a single sign factor which is raised to an odd positive integer, reserve one sign factor and convert the others to cosine factors. Then expand and integrate. So you're creating a situation where you'll have a g of x, or whatever your variable is, and then your g prime will be ready to go, or almost ready to go. All right, so here we go. We've got the sine function cubed, and the angle is 2x. So this will be equivalent to the integral of sine squared at 2x times sine at 2x dx. So this is the one on reserve. So then we'll have the integral of 1 minus cosine squared at 2x times sine at 2x dx. So our g of x then is going to end up being equal to cosine at 2x. So g prime at x will be equal to -2 times sine at 2x with times dx. So next we'll go ahead and multiply through by the sine at 2x dx, and then we'll have sine at 2x dx, which is fine. I know it looks weird, but it's fine. We have an antiderivative for that one. The one we needed to reserve an antiderivative for was the second term. So minus the integral of cosine squared at 2x. Actually, I'll write it the other way. Cosine at 2x, the quantity squared, times sine at 2x dx. So the very first one doesn't need the g of x, g prime of x thinking. We've already got an antiderivative for that one. But the second one, it needs a factor of -2 to have our g prime. So I can change the minus to a plus and multiply by 1/2. And so our g prime for that part of it is here. So on the first one, you just use a general trig rule, and you're going to need to adjust it because you've got a 2x in the power. So I'll multiply by 1/2. And then integrating, we'll have 1/2 negative cosine at 2x plus 1/2 times 1/3 cosine at 2x, the quantity cubed, plus our constant of integration. So it's kind of weird because it's a mix of different things. So that gives us -1/2 times cosine at 2x plus 1/6 times cosine at 2x cubed plus our constant of integration. And we're all done. Groovy? All right, now let's take a look at integrals involving only one cosine factor, which is raised to a positive odd integer. So if you have a single cosine factor raised to an odd positive power, Reserve one cosine factor and convert the others to sine factors. Then expand and integrate. So very similar to what we just did, just switched around. All right, so here we go. This will end up being the integral of cosine at x to the fourth times cosine at x dx, which is the integral of cosine squared at x squared times cosine at x dx. You got this, I promise. Which will be changing into sine factors. 1 minus sine squared at x, the quantity squared, times cosine at x dx. And then expanding out this part will be 1 minus 2 of these sine squared at x's plus sine at x to the fourth times cosine at x dx. Now multiplying cosine at x dx through. The first one will just be one of those so easy it's hard integrals, right? You have a formula for it. Minus 2 times, we have the integral of sine at x squared times cosine at x dx. So these are all multiplying to that. The dx goes with each term. And then plus the integral of sine at x to the fourth times cosine at x dx. So for the second two integrals, g of x is equal to sine at x. And so g prime at x is equal to cosine at x. So we have it already, right? So we'll have the very first one this doesn't apply to. This is just going to be sine at x. The antiderivative of the cosine function is the sine function. Minus 2 times, well, sine at x is going to be cubed over 3, just using that power rule, plus sine at x will now be raised to the 5th power over 5, plus our constant of integration. And then we'll have sine at x minus 2/3 sine cubed at x plus 1/5 sine to the 5th at x plus our constant of integration. Groovy? So you see what's coming up next. Go ahead and take a break. If you like this video, please hit that like button and subscribe. You can share it if you want. I hope you have a wonderful morning, afternoon, or evening whenever you are watching this show. Bye.